All right, everybody, we're going to get started. So thanks for everybody for showing up. I'd like to thank our regular sponsor, who's Cloudera. They sponsor the meetup, and usually they sponsor the food, but this time they didn't. DataStax who's the, what would you say? They're not the creators, they're the commercializers of Cassandra. Well, they're the sponsor of the pizza and the drink tonight, and they also provided a lot of they provided these swags. So if anybody hasn't gotten a T-shirt or a sticker yet, I strongly urge you to do so because Brent doesn't want dozens of Cassandra shirts around. So we have some upcoming meetups. The March meetup is American Family, kind of how they went through and fired up a Hadoop cluster and did like a proof of concept on that. April and May meetups are kind of heavy on data science. And we have everything scheduled out through hopefully now October. So if people have other topics, I'd love to hear from you guys. It's always good to kind of keep momentum going. There's a lot of topics going on in the big data ecosystem, and we're trying to highlight or focus local companies or Wisconsin companies and how they are using big data tools. Just because I think that's a topic that's of interest to a lot of people and it gives those companies exposure. So anyway, at this point, I'll turn it over to Brent Theisen, who's from Womply and who's going to be talking about Cassandra. So there you go, Brent. Thank you.
Thanks, Pitt. So just before I get started, just want to keep things informal. So if at any point during my talk you have a question or something, just feel free to get my attention and I'll do my best to answer it. So welcome to Deep Dive into Apache Cassandra. Just give you a little background on who I am and where I work. My name's Brent Theisen. I'm a principal engineer at Womply. Womply is a startup based in San Francisco that uses data to grow, protect, and simplify small businesses. And so one of the ways we do that is by obtaining transaction, weather, and third-party site data that's relevant to our small business merchants. And with that data, we provide brick-and-mortar merchants with products and analytics that improve their businesses and help them grow. And so you can see the little snippet to the right there. That's a very small screenshot of one of our products, just very basic time series graph of revenue for one of our merchants, and also weather for the given data point, as well as some comparisons against other pizza restaurants within their geography. So that whole snippet, for the most part, is stored in Cassandra. We've been using Cassandra at Womply now since August 2013, and we've had a really good experience with it. So just to give you some background on Cassandra and how it came into being, it was originally developed at Facebook around 2008. The name Cassandra actually comes from a Greek mythological prophet that was cursed with accurate predictions that no one believed. So there's a couple theories on why the developers chose that name. One of those theories is that the developers believed that the move to NoSQL was inevitable, but few people realized it, and so they stuck to their relational databases. Another theory is that Cassandra was a cursed oracle, and there's a company within technology that we have all heard of that is also named Oracle. Many in the Cassandra community consider Oracle to be somewhat of a rival technology in some respects, simply because a lot of people throw big money at Oracle and try to build out their infrastructure with it when really they might be best off using something like Cassandra. So initially, the developers modeled Cassandra after the Amazon DynamoDB and Google Bigtable papers. So a lot of the core concepts, at least in what began to be Cassandra, came from those papers. In 2008, Facebook decided to open source Cassandra on Google Code. In 2010, Apache made it a top-level project. And today it's used by hundreds of companies, probably the biggest of which is Netflix, which uses it to power most of the storage for their products. And then, of course, Twitter, eBay, and also the game Call of Duty records a lot of the user interactions within their game with Cassandra. So why might you use Cassandra? There's several different reasons. First, right off the bat, If you need to store terabytes of data, Cassandra is probably something that you should look at. It's built to scale from the ground up, so it's a good choice there. Also, if you need to perform a high number of writes per second, so if you have data that's coming to you from something like Storm or Kafka or any of those types of products, it's also a good choice because you can obtain that high throughput on writes. If you need to perform key-based queries in what I call real time here, I use quotes with real time simply because, like, if you talk to embedded developers, there's a good chance that they have a different interpretation of what that means. For the sake of this presentation, real time to me means like an OLTP query. You need a sub-second, obviously, response, if not, sub, 100 millisecond response. So if you need to perform those key-based queries in that sort of time frame, it's a good choice. Also, if you need to run massive parallel processing jobs, so what I'm getting at there is like Hadoop and Spark, it's a good choice. If you need to replicate data across multiple data centers in full duplex, that's something it also does very well. So if you have data center 1, on the East Coast and data center 2 out on the West, you can set up Cassandra clusters in both and have writes in data center 1 go to data center 2 and vice versa. It's a full duplex replication between those two data centers. Also, and finally, if you need to scale horizontally in a predictable way. So what I mean there is if you want to use commodity, hardware or virtual machines and want to have a good idea of just how much bang for your buck you're getting when you buy those, like based on, obtaining a virtual machine of a certain size, like an EC2 instance, how many writes per second does that give me? You can actually do that with Cassandra. So what can it run on? It's written in Java. It targets the Oracle Java 1.7 JVM. I realize that 1.8 has been out for a while now, but there are a number of things that need to be addressed in the current Cassandra code base in order for that JVM to be supported. So right now it's Oracle 1.7, which means it can run on Windows, Linux, OS X, just about anything that's Unixy. And on the client side, there are drivers available for a bunch of different languages, some of which you see here. And the support on the client side, it extends through a number of different languages. But having said that, not all languages have clients that support the latest features in Cassandra. So you really want to make sure that whatever language you're planning on using is well supported on the client side. There's also support for massive parallel processing frameworks like Spark and Hadoop, as I had said earlier. So it can run on all those different platforms. As far as installing Cassandra, there's not that many different distributions of it. If you want to get the binary distribution, which is the case most often, you probably want to choose from one of either DataStax Community or DataStax Enterprise. They provide things like RPMs and I think DEB files, and I believe Windows MSI files, although I'm not sure about the Community Edition. So they can, and those, with DataStax Community, what you're getting is basically stock Apache Cassandra. With the Enterprise Edition, it's a paid product, so you're going to have to work out licensing costs for it. But it comes with a number of bells and whistles that you don't get just in the vanilla version of Cassandra. For example, there's support for Solar. They also have support for Hadoop, MapReduce, Hive, Pig. So something to think about there. But if you're just getting into Cassandra, I would say DataStax Community Edition is probably a good first choice. There's also the Apache source distribution that you probably want to stay away from unless you're just looking at the source to figure out a bug or a potential question you have about the code base. Really, you probably don't want to deploy with it. So, and you want to also try and stick to whatever the latest stable version is, as reported on Apache's site. Right now, that's 2.0.12 is the most stable version, whereas the latest version is 2.1.3. There's also support for Docker, Bash, Chef, Puppet. So if you want to provision your VMs use with Cassandra, using any of these tools that's available, and I highly recommend it. It's really important that when you need to add a node, you can do so programmatically or via some deployment mechanism automatically, rather than having to go through some manual process. And finally, development environments should be provisioned as closely to production as possible.
What Docker, Bosh, Chef, what are those?
So Docker is a tool for building images. So you can basically with Docker you can run a virtual machine like instance and then take a snapshot of it, and that becomes an image. From there you can share that image. You can deploy it on any number of different machines. So yeah, and Chef and Puppet, those are configuration management tools. So if basically by provisioning, I mean they're installing Cassandra and also configuring it, starting it, starting the daemon, those sorts of things. So yeah. And as far as development environments, you really want to have those as close to production as possible. That's kind of a general rule of thumb. Docker and Vagrant are your friends there. So like, for example, with my setup right now, we're using Chef to provision. We're starting to make the move to Docker. But when I work locally, I'm always using a Vagrant virtual or Vagrant box that contains my Cassandra server. And from there, I actually interact with the Cassandra server locally in that virtual machine. So it's as close to production as possible. So configuring Cassandra. Almost all configuration options are set in a file called cassandra.yaml. And so I don't know if some of you have seen YAML, but the syntax is a little bit different than some of the other things out there, but it's pretty easy to pick up. Some of the more important options in cassandra.yaml are the seeds option, which basically allows you to list a set of IPs that new nodes should contact whenever they come up. So for example, let's say I already have a cluster of Cassandra servers and I want to add a new node to it. What the seeds configuration option lets me do is specify which existing nodes in the cluster my new node should talk to get information about the cluster. So with Cassandra, one of the pieces of magic with it, if you will, is that it has a gossip protocol, a peer-to-peer protocol. So all the nodes in your Cassandra cluster are talking to each other via this back channel. What seeds does is allow a new node to know the initial nodes that it should talk to get information about the cluster. Another setting is the endpoint snitch, which is basically just a Java class that informs Cassandra about the topology of your network, and it helps to allow Cassandra to efficiently route peer-to-peer requests. So with Cassandra, I mentioned earlier, you can run Cassandra in multiple data centers, right? You can have data center 1, data center 2, data center 3. And those might exist in different AWS EC2 regions or different availability zones. What the snitch is doing is basically figuring out that this set of machines is in this data center over here, and this set of machines is in another data center. So it's automatically determining how your data centers, your Cassandra data centers, should be mapping to nodes in the cluster. So a couple of options on what snitch you can use. The rack inferring snitch is simply just looking at your IP address on each of the nodes and taking the first 2 octets and saying any nodes that have the same first 2 octets are in the same data center. The property file snitch basically allows you to do that mapping manually via a Java property file. And then the EC2 snitch will actually figure out what availability zones you're in, each one of your nodes are in. And from that, it'll create a data center for each availability zone you're in. One snitch I left off is the EC2 multi-region snitch, which is basically the same as the EC2 snitch. It just provides that greater capability of being able to determine the regions that you're actually in if you use AWS. So initial token. With Cassandra, you have a choice. You might see on like some of our swag here on the title title slide of my presentation here, you see the symbol of a circle with a bunch of nodes around it. The initial token, and what that circle is referring to is a key ring, which we'll talk about in the next slide. But what initial token is doing here is basically setting for this particular node what the start of the key ring is going to be that it owns. So if you think about primary keys, in Cassandra we use primary keys for everything that's stored. We can use consistent hashing against those keys to come up with a hash digest of that key. And because it's a hash digest, we know the upper and lower bounds, the possible values there. So what this is doing is allowing you to basically tell a node, you own this piece, this set of keys from here to here. Except it only knows the start, it doesn't know the end, because the end is determined by the next node with the next highest token. And so num tokens, keep in mind, initial token and num tokens are sort of mutually exclusive. Either you do one or the other, you don't do both. With num tokens, basically you're saying you want to use what's called a virtual node cluster. So you're specifying the number of individual ranges in the key ring that this node should be a part of. If we move to the next slide, we'll see this in a more graphic way. So this diagram depicts those two different setups, right? Those two different types of key rings. So on the top half of the diagram, what you're seeing here is a ring without virtual nodes. So you're basically, in the configuration file, you're setting initial token to be the starting point of the range that this node owns. And this is kind of an old school way of configuring a Cassandra cluster. Nowadays, most people use virtual nodes, which are depicted on the bottom half of this diagram. With virtual nodes, what's happening is every time you add or remove a node, there's a partitioner in Cassandra that figures out which parts of the key ring that this new node owns, or which parts of the key ring that we have to move to other nodes because we removed a node. And so you can kind of see this here on the bottom half. This is a 6-node, in both cases, this is a 6-node cluster. So you have 6 different machines in each one of these clusters. And you can see, for example, on the top half where we're hard coding, if you will, our initial token, that in the circle, there's a letter A in the circle here. That's a token range. So that's part of the possible space that could contain different pieces of data. That token range set of data is actually stored on the top half of the diagram on nodes 1, 2, and 3. You can see that they each have letter A inside them. And that's because what's happening there is replication. We've set a replication factor of 3, so that means that part of the key ring is being replicated to 3 different machines in the cluster. And down on the lower half, you can see something a little bit similar, although more granular. The A node is in a different position on the ring here, but again, it's replicated on 3 different nodes 1, 2, and 5. So same sort of thing, between virtual nodes and the 1 range per node, but the difference is that when you set initial token and you use a single range per node, what you're basically saying is that every time you change your cluster, you add or remove a node, you're going to have to go through and determine for each node in your cluster what the new ranges are. Whereas with virtual nodes, it's doing that all automatically for you. It's saving you from that. When you add a new node with virtual nodes, there's no changing, initial token value or anything like that. All you're doing is, telling it the number of tokens it's responsible for, and that's it. From that, it can rebalance the data such that the new node has, roughly the same load as the old, as everyone else in the ring. So it's a pretty core concept of Cassandra key rings, and we'll talk about that a little bit more. So some Cassandra command line interface tools. So there's really two big ones. There's what I call SQL shell. SQL shell is, just like pSQL in Postgres, or the MySQL command line interface. Basically, it just allows you to perform queries against nodes in your cluster. So Cassandra comes with a query language called Cassandra Query Language, which we'll see a little bit later. But whenever you run Cassandra Query Language queries manually, that's often done with SQL shell. Then you have Node Tool, which provides a number of subcommands that are useful for administration, monitoring, and basically figuring out the state of the cluster. Really, with Node Tool, all it is a JMX client. So I don't know if some of you are familiar with Java, but Java has a library called API called JMX that allows for telemetry, and basically you can use it to get information from a running server about how it's operating. Node Tool is just a JMX client. So if you're in the know on JMX and you want to, I suppose you could write your own JMX clients as well for whatever monitoring tasks you have. So, and at the bottom here, I include the results of probably one of the most basic commands that Node Tool provides, called status. What you're seeing here is that, first of all, we have one data center called Data Center 1. There's 3 nodes in this cluster, and you can see that they're all up based on the UN in the first column. You can see their IPs. You can see their load, meaning the amount of data that Cassandra is storing on that node. Then you see tokens, and each one of these is 256, which means that the num tokens value that we talked about earlier in configuration was set. If you were dealing with a single range per node cluster, that would be 1. So we can tell from that we're using virtual nodes, and that each one of our nodes has 256 tokens, that token ranges it's responsible for. Then there's the owns percentages. You might notice that all these are roughly 66.6%, and all 3 of them, of course, add up to 200%. That, again, is because we have replication going on here. So in this case, we have a replication factor of 2. And then host ID and rack really aren't there isn't much to talk about there, so I'll continue on. Yes?
With 256 tokens, does that imply you can't have more than 256 servers in that cluster ever?
No, not at all. In fact, basically, as you add nodes, it's adding those numbers together to figure out the number of token ranges in your ring. Yep. So that's a flexible thing. Virtual nodes are a really good thing, and that's one reason why. So Cassandra data model. So now we'll start getting into the query language and aspects of how you actually use this thing. So Cassandra's data model is kind of similar to like some relational DBs, in such that we have key spaces, which are also known as schemas. Those key spaces contain tables. When you create a key space, one of the few things you have to do when you create that key space is determine a replication factor for it. So you've heard me use the phrase replication factor, and hopefully everybody knows what it means, but it's basically you specify the number of nodes that should contain any piece of data. So how many times do you want this replicated in your cluster? That's controlled at the key space level. So when you create your key space is generally when that is set. Actual data that you persist with in Cassandra is stored in tables. The old school phrase for tables is column families. It's still used, like if you can use column family and table interchangeably in SQL shell in some cases. But for the most part, people nowadays are calling these entities tables, not column families. So tables must have a primary key. I mean, unlike some data stores that allow you to get away without one, there aren't that many use cases for it, but some do. Anyways, Cassandra, you must have a primary key. You cannot store data You can't create a table without specifying one. With Cassandra, natural keys are preferred for these primary keys, but you can also use universally unique IDs in place of a natural key if the data doesn't support a natural key. So that's available for you too.
Why are natural keys preferred?
I think we'll see in a little bit, but natural keys, generally speaking, when you go to query Cassandra, you're asking for, like in the case of our users table, we'll talk about in a bit, you're asking for like a username generally. And it fits a lot better. With a lot of relational databases anyways, if you're coming from that world, like Oracle or MySQL, a lot of them have sequences or like auto increments, sometimes they're called. Cassandra doesn't have that per se, so you don't have sequences in Cassandra. And so that's one reason why. There is kind of a substitute for sequences, which we'll talk about in a bit, called time UUIDs. But yeah, for the most part, I think it's because of that. So you can use several columns to form a compound key, and that's something that's frequently done. You often see primary keys consist of more than just a single column. Instead, sometimes you'll see 2, 3, 4 different columns composing a primary key. So how you structure your primary key determines partitioning. And so what I'm saying there is that when in that key ring that we showed earlier, what's determining where the data gets stored is the primary key. So how you define your primary key becomes pretty important as far as avoiding things like hotspots. So it's something that when you're doing data modeling with Cassandra and probably a lot of other data stores, your primary key means a lot. And so the primary key is really the only thing that's required. If you wanted to, you could have a table consisting of nothing but columns that are in the primary key. There's nothing that says you must have a column outside of it. So, and there are some use cases for that. So here's our first glimpse of a CQL query. We're creating a key space, and as you can see here, I mean, there's not a whole heck of a lot going on, but there's some in the way of replication. The first thing right off the bat is create key space, my_key space. You're specifying a name for your key space, but other than that, everything else is replication related. And so you can see the class we're specifying for our replication is network topology strategy. There's two different types of replication strategies in Cassandra. So there's two different things that govern how data is replicated, or strategies that govern it. The first is you can choose to use is the simple strategy, which is really for a single data center only. If you go to try and take a key space and the cluster containing the key space and make it so that there's another data center that replicates that key space, you'll find that you can't, because you have to use the network topology strategy for that. So the network topology strategy allows for multiple data centers. Really, as a rule of thumb, you should really be trying to use the network topology strategy, just because it's such a pain to go back and deal with the key space that doesn't support replicating across data centers when you decide that you add one. So it's a good idea to stick with network topology strategy. Also in our CQL, you can see after the class, we have data center 1:3. So what we're saying there is that data center 1 should have a replication factor of 3. So there'll be 3 nodes in data center 1 that contain the same data, the same replicated data. And then the next statement being data center 2 has a replication factor of 2. So the same idea there, it's just 2 instead of 3.
Question.
Yes?
When you say nodes from now on, we're mapping it to a machine, correct?
Yes. Yeah, we are mapping it to like a virtual machine, or I suppose a regular one. Yep. Yeah, when I say a node, I'm talking about a machine. So in this case, with data center 1, there would have to be at least three nodes in data center 1 for this create key space to make sense, because we'd have to replicate it 3 different machines. And even 3 nodes in data center 1 doesn't make a lot of sense, because they're all a clone of one another, so you really want to distribute your load. But yeah, when I say node, I mean virtual machine or a regular one. Yes?
So is the replication factor guaranteed, or is that going to depend on the partitioning with your
So,
primary key?
sure, yeah. So the partitioning of the primary key doesn't really affect replication, but the consistency aspects of a distributed data store like this do. So what I mean by that is, if a node is down, like let's say you just did shutdown on one of your nodes and you just started persisting data, chances are it's going to own some areas of the key ring that it should be replicating, but it can't, obviously. So something like that would prevent it. But then when it comes back up, we have mechanisms we'll talk about that ensure that it comes consistent. So yeah, cap theorem aside, yeah.
Just excuse me. So is the primary key across different table needs to be the same?
So
So the question was, is the primary key, should it be the same on multiple tables?
Yeah.
So no, not necessarily. It really depends on your use case. And as we'll find a little bit later, queries in Cassandra don't support joins. So I don't know if that's kind of what you're getting at. Should the primary keys be similar in order to do joins? And no, not necessarily. They can be much different. Yep. So now that we have a key space, we're actually going to create a table in it. So the first thing that I'm doing here in SQL Shell is issuing a use my key space statement. All that's doing is changing the current key space that we're working in to the one we just created. And then after that, I create a very simple table called users. You can see here that users has a username primary key followed by 3 different keys containing various user information. So yeah, the CQL in a lot of respects is pretty similar to what you might be accustomed to with SQL in the relational world. And you can kind of see that here. Of course, I have to note that the username primary key is going to define how that data is partitioned and indexed. So as far as the partitioning aspect of that, that means that if I have username Brent, that username Brent is going to determine which nodes or where it falls within that key ring, and subsequently what nodes it gets put on when it's persisted. So while we're on the subject of create table, let's talk about some data types, specifically scalar ones. So you can expect to have access to all the usual suspects that you've been used to working with. Things like Boolean, text, int, those are all there. There's also a counter data type, which is kind of unique to column-oriented databases, I guess. So counters basically allow you to increment and decrement, but you can't actually set a real value. So like I can say add 100 or subtract 100, but I can't say set it to 100. The reason why is because with counters, what you're doing is if you wanted to set an absolute value, you'd basically normally you'd have to perform a read-write for this operation, right? You'd have to read the existing value, add 100 to it, and then write it back. Counters actually allow you to perform that same operation without having done the read, just the write. So it's kind of an interesting type. However, I want to caution you a little bit about it. That throughout Cassandra's history, this type has been around, and it's like one of the few things that they've had a lot of problems nailing down. In the case of counters here, they ended up finding a problem whereby counters can drift from the real value they should be. They claim to have had fixed that in the most recent version of Cassandra, but you really want to do your due diligence on it before you start using something like a counter, or using a counter. You can also expect to find var ints and decimals, which are just variable precision integer and decimals respectively. There's also an INET type. You can store IPv4 and 6 addresses. Timestamp, pretty similar to what you've probably been used to using. Time UUID. I mentioned this earlier when Pitt had asked me a question. So time UUID is actually what they call a type 1 UUID. And so that basically says that it's a 128-bit value. The first, I think it's like 40 bits of the value are the time down to the nanosecond that it was generated at. The remaining parts of it are for dupe prevention and also the MAC address of the node it's on. So basically what you're getting here is you can use the SQL now function to guarantee that an ID is unique. Like if you really only want to use a type like this in a primary key more than often, more than not. And so when you specify now, what you're getting is guaranteed uniqueness, but also when you go back to read that value, you can actually get the time that the thing was generated at, which for some use cases is pretty useful thing. There's also a regular UUID type, which is basically the same thing as time UUID. It's just doesn't provide the now function in SQL, and you have to generate your own. So those are some of the scalar types that you can use in create table. There are also what are called collection data types that you can use. So you can actually have columns that that contain a list of items. So with the list collection data type, you can store whatever elements you want in whatever order you want. And you can control the order of those values in the list by adding and deleting values or overwriting them by index, where you can just prepend them or append them. You can also remove individual values. And so those are some pretty useful things when you're modeling more complicated use cases. When you actually go to modify a table or create a table, you actually have to specify the type of your list. So like in this alter table example that I've got up here, the type is timestamp. So every single element in that list must be a type timestamp. Some of you who've seen parameterized types and stuff like that might think that there's some cases where inheritance applies or something like that just because of the angle brackets. No, you have to specify one type for your list. There's also a set collection data type, which is basically the same thing as a list. It's just in sets. They're unique elements, right? And they're in natural sort order. So other than uniqueness in the sort order thing, though, it's the same as the list. And you can see the syntax is pretty much the same in your alter table. And finally, the map collection data type allows you to store key value pairs. And you can, obviously, like most maps, you can set and delete them, by key. And when you go to specify, when you go to create, this should read set down at the bottom. The last alter table there should read, it should read map, where it says set. But you get the idea. You're specifying a map where the key is the timestamp and the value is some text. So, number of options for data types, or collection data types. There are also, new in Cassandra 2.1, there are also user-defined types, which more often than not are used to store denormalized data that you might normally store in like another table. So with Cassandra, when you go to data model something, denormalization is usually the word of the day. You usually want to look with an eye towards it when doing your data modeling. You want to have the data that you need to have together stored in the same table because there's nothing like SQL joins. So this is one thing that helps you kind of accomplish that, right? And I have an example here. So I create a type of address, that has the normal columns. It also uses a collection type for the phones column there. You can see I have a set of phone numbers. And I add a addresses column to my users table. And that column is a map that is keyed on text and then the address type that I just declared. And so the idea being there that I could have a map that's keyed on text because I want to specify whether it's a home address or a work address or whatever. And then the actual address information on the value side of that. One thing to note, you see that frozen keyword there. What that's saying, it's kind of it's there to make you realize that the components of your type are all being serialized into a blob and then persisted into, in this case, on the map value side of the map. So when you go to persist a type, you should have all the data for that type already. You can't just say, street equals 1 Main Street and expect to maintain all the values from city, zip code, and phones. It'll overwrite them if you don't specify it over again. So, I don't know, user-defined types are pretty new. I don't know if I'd recommend them yet. I haven't used them myself, but something to think about.
Question?
Yes.
So for the container types and the user-defined types, are you able to do queries within Cassandra on them?
Usually, no, the primary key is usually the one thing that you're querying on. So only components in the primary key, because it's built to scale. It doesn't really allow you to specify criteria outside of it. So, yep.
So is frozen required for user-defined type?
It is for now, yeah. I tried doing it the other way. It wouldn't let me. It gives me some sort of error about, I can't even remember. But yeah, frozen is required.
Yeah.
It's, yeah.
If you have many of these, like addresses and preferences and what have you, whenever you read it for a single user, it's got to read all the blobs attached to it?
Not necessarily. So the question was, when you go to read a row from the users table and there's a bunch of addresses in that row, does it have to read all of them? My answer to that is it does have to scan over the data, but it doesn't necessarily have to read it into memory and then send it on up to the client. So yeah, it depends on whether you actually specified you need it or not. So, yep, good question. So now going back to our example, we've created a key space, we put a table in it called the users table. Now it's time to just insert some simple data with CQL. So the first thing that you see here is consistency 1. What I'm telling SQL Shell by specifying that statement is how many nodes should receive whatever queries I'm about to run after it before that query returns successfully. Okay, and we'll talk about that on the next slide, but basically I'm specifying a consistency level. And then from there you can see I'm just doing a pretty simple insert, right? I'm just inserting a username Alice with an email address and a first and last name. The syntax you see here is pretty close to what you might expect in other, SQL-based dialects. So let's move on to the next slide about that consistency 1 that we just specified. So consistency levels in Cassandra basically specify how many nodes need to process a read or a write statement before that query returns successfully. And so if you think, if some of you might be familiar with the CAP theorem, right? The notion of consistency and availability, partition tolerance, pick 2 out of the 3. What you're getting here with consistency levels is tunable consistency. So you can play with that gray area between consistency and availability. And you can, as we go through some of the options here, I hope you see that. The first set of options that I've got here is 1, 2, and 3. So real simple, right? I mean, what's the exact number of nodes that Cassandra should ensure that the query ran on successfully before it tells you that it's good to go? Then there's also local 1 which is pretty much the same as the regular one that we just talked about, but with the caveat that that read request is only going to be sent to nodes within the local data center. So if you have data center 1 on the East Coast and data center 2 on the West Coast, with local 1, if your query originated on the West Coast, it's going to stay there. It's not going to go over the VPN or whatever. Then you have quorum, which is just a quorum of nodes must reply. So a quorum is, the replication factor divided by 2 plus 1. So if you had 3 nodes, then your quorum would be 2. And then you have local quorum, which is the same thing as quorum. It's just, it confines itself to that local data center again. So it doesn't go over, to other data centers and ask for results or to persist the read or the write. And then you have the all consistency level. This is basically the highest consistency that you can get with Cassandra. What you're saying is that if the query fails on any one of the replicas that for this key, that the whole thing should be returned, should fail, and that all the other nodes should not persist their data. And then finally, you have the opposite end of that. You have the most availability you can get, but with the least degree of consistency that you can get, and that's the any option. So any actually only applies to writes. So when you go to do a write with any, what's actually happening behind the scenes is the node that received your request, which could be any one of the Cassandra nodes in your cluster, because Cassandra is peer-to-peer, any one of the nodes in your cluster could be receiving these queries. They can all act as what's called a coordinator. But that coordinator receives your any write. You tell it to write an any, or you tell it to insert some data with any. If the coordinator can't find a replica that's up that should be owning that data, it'll store it itself. And then when a node comes up that's available, that's supposed to own that key, it will see that it comes up from the gossip peer-to-peer protocol. It'll be notified of this node coming back up, and it'll send the data that it persisted for this any consistency level up to the node, to the replica. And so the replica, even though it was down when the write was issued, the replica will still receive the data and become consistent. And so this process is called a hinted handoff, and we'll talk about it a little bit more later on here. All right, so earlier we had done an insert. Here you see an update. The update is, inserts and updates in Cassandra are the same thing. Whether you do an insert or an update, doesn't matter. Because everything is key-based, you could use either type of statement and achieve the same result. And so, for example, you see here that we're updating users and we're setting an email and a first name for a user named Bob. Well, there aren't any columns or there aren't any rows that specify that primary key of Bob because the last user we added was Alice. And so oftentimes you hear people in Cassandra refer to writes or upserts just because whether it's an insert or update doesn't matter. Cassandra isn't doing random I/O like you might find in a relational database where there is a distinction between an insert and an update.
In this case, username is the primary key.
Correct. Yep. Same table as before. Yep. Same create table as before. I'm just adding another row to it. So now we got 2 rows in it.
So there's no concept of a
Yeah. No. There's no concept of a like. There's a lot of limitations to CQL to achieve the kind of scalability that they're striving for. They make a lot of concessions on what you can do with it, and that's one of them. There's no like indexing. It's not going to be able to do a like query. All right. So now that we've done an insert and an update, let's get into the nitty-gritty of what's actually happening behind the scenes when those occur and go through the anatomy of a write. So the first thing right off the bat is your client, in this case, let's call it SQL Shell, sends a query to a node. Remember, it can be any node. Doesn't matter which one. They can all act as coordinators. In this case, the coordinator role, the coordinator node will identify as number 10 there, the yellow circle in the ring. And
How does the client find a node at all?
so remember, generally speaking, when you set up your client, you're going to pass it an IP address, and that kind of acts as kind of like the seeds node or the seeds configuration option I talked about before. So when you run SQL Shell, you do have to pass it the IP of at least one of the nodes in your cluster. From that, though, I mean, if you wanted to, when you run SQL Shell, you could pass more than one. You could pass, all the IPs, and what it would do is cycle through each one of them. What's interesting is about some of these CQL clients is that they're very smart. So they know that your last query returned, 10 milliseconds, later than the same kind of query that it ran on this other node, and they both have the same replica data. It'll choose the faster one. So sort of an interesting thing. But yeah, you do have to specify an IP to SQL Shell when you run it, or multiple.
Does it make sense to specify all known nodes, or would it be better to specify like 3?
Oh.
Basically, if any one of those nodes go down, you're doing 2 calls, right?
Absolutely,
The
yeah.
client will say no to that one. Maybe take it out of the ring.
Yep. So I specify all of mine. In my client code, the actual code I write that interfaces with CQL, I specify every single IP I have in my cluster. And yeah, it works exactly kind of how you were mentioning. When a node goes down, the client is smart enough to see it, similar to how the servers are smart enough to see that too. So it's a pretty seamless thing usually. Fault tolerance is a pretty core concept of Cassandra as well.
That's a question.
Yep.
So bundled with this Cassandra project is client code then? Client code that
Yep.
is reliable and smart? Is that what
Yeah, so Cassandra is a client and a server. The server acts as a distributed database. So you have multiple nodes that each hold a slice of the database, if you will. And the client code, yeah, it talks over a custom protocol. The client and the server communicate via something called SQL v3 binary protocol. If you're ever interested in that sort of thing, I've got code from like 2 years ago that's all in C that implements basically SQL Shell, but with the old school stuff. But yeah, part of Cassandra defines a wire protocol for exchanging information between client and server. There's also one for gossip, as far as the wire protocol used by client or by nodes in the cluster to talk to one another. So yeah.
Are those protocols in separate libraries? Are they open source? Are they like multicast where you can say, hey, I want to have this thing have Ghost?
In the case of SQL, in the case of client to server, yeah, I mean, all this stuff is open source. It's all under Apache, but I doubt you'd want to reuse it for anything. They are using a Java library I can't remember right now that basically allows you to define your own language. But that's part of what they're doing with CQL's protocol. As far as the gossip protocol, I'm not sure there. I'd have to look that up. I really don't know.
Is it, if you were to upgrade, let's say, I've seen some tech do this. If you had to upgrade, the version and upgrade the node, does it send, the needed jars through the protocol to upgrade the virtual machine?
Nope. Yeah, I think you're probably getting at Hadoop or Spark or something. Yeah, so Louis is asking if you have to worry about, when you upgrade a cluster, do you have to worry about shipping jars between nodes in that cluster? Generally, when you go to upgrade Cassandra, if it's a release level upgrade, what they recommend doing is what's called a rolling restart. So what you're doing is you're shutting down one Cassandra node, you're applying whatever the upgraded Cassandra is, and then you'll bring it back up, make sure it's in the cluster, and you do that for all the nodes in your ring. So yeah, there's no worries about shipping code across or anything like that. Yep. All right, so back to the right thing. So our client has sent a CQL query to a node. It is now acting as the coordinator. You can see the yellow dot number 10 there, receiving the query. Once the coordinator gets it, the coordinator is smart enough to know the topology of the key ring. So it knows, based on the key that you're writing, where that data belongs, which nodes it belongs. Those nodes are identified in the diagram as R1, R2, and R3, also as 1, 3, and 6, I guess. So it's smart enough to know what nodes own that data or should own that data. So it immediately, upon getting that CQL upsert, sends a write request to each one of these 3 nodes at the same time. So it's using thread pools, right? It's saying, all right, let's send this out to all the different nodes, and it's kind of working a little bit asynchronously here. So it sends that read request out to the 3 nodes. In this case, we're saying the consistency level is 1. So all we need is 1 node to come back and say that the write was successful. And so the first node to respond wins. And that, in this case, it's node 1 that responds first. And once node 1 responds, the coordinator sends back a response to the client saying, hey, this data's been persisted. So
what happens? Does the coordinator then ignore the response coming from 3 and 6?
It's an excellent question. So the question was, now that the request that the coordinator was handling from the client has been satisfied, what happens to the responses from the other replicas that are saying whether they received the write or not? And so the answer there is, if one of those 3 nodes says it's failed, the coordinator will add, or if one of those other 2 nodes is down, what will happen is the coordinator will set up what's called a hinted handoff, which we talked about earlier. Basically, it writes a hint in one of its local files on the coordinator that says, when node 3 comes back, I need to tell it about this data that it needs to have, that it didn't get. So, and that kind of goes in the last bullet point here. What happens when one of these nodes are down? Hint and handoff is one of the ways that a down node could receive the data it missed. There's also what's called a read repair, where when you actually, when you do a read against data that isn't up to date on one node, the coordinator sees that and tells it, hey, no, this is the right data. So that's a read repair. And there's also node tool repair, which is a command that you're often recommended to run, set up a cron job for on the nodes in your cluster that actually does a lot of legwork in making sure that your key ring is consistent. So there's those 3 different means for Cassandra to make sure that nodes that are down receive the data that they should have when they miss it. So we've talked about how this all works from a distributed perspective. What actually happens on a replica node when you persist data? So let's say we're dealing, back on our first graph, or first diagram here, we have node 1. Let's say we're looking at node 1, or 3, or 6, right? What are they actually doing? So the first thing that happens when a replica receives a write request is that it's going to write the write request in a commit log. And so the commit log is a file on persistent storage, sequential log that's just being appended to over and over again. So the replica writes that write data to the commit log. So that way, right off the bat, if the machine goes down, once that commit log has been updated, it knows to replay the commit log when it comes back up. So right off the bat, we go into the commit log, the data goes in the commit log. From there, it goes to something called a mem table. And so a mem table is basically just a structure in memory that holds data that has been written to this replica for a given Cassandra table. So mem tables are specific to a Cassandra table. If you have 3 Cassandra tables and each one of them has been getting data, you'll probably have 3 mem tables in memory for a replica. So once it gets into a mem table, it's going to keep adding and adding new data to this mem table until it exceeds a configured threshold, whatever you configure. And then once it exceeds that threshold, it gets flushed to disk in a file called an SS table. And you can see that depicted here. So an SS table has an index, and it has also row data, as we'll see here in the next slide. So SS tables actually stand for all right. So SS tables actually stand for sorted string tables. They only similar to mem tables, they only contain data for a single Cassandra table. And we call them sorted string tables because they're sorted by row key and then also column key, as we'll see in the next slide. Once an SS table file has been written, they never change. They're immutable. By default, the contents of all the data that's in that SS table file is compressed using a library called Snappy. And Snappy basically just favors performance a little bit over compression results. So it's a little bit faster than some others out there. But and a replica will often have several SS table files for a given SQL table. So if you look at where your data is actually going on disk, on the file system of all your different Cassandra nodes, it's in these SS tables. And we can see here's an example of like some of the sorting aspects of an SS table file. You can see here we have our Alice and Bob rows that we wrote earlier with an insert and an update. You can see that the first row, Alice, is the first row in the SS table file, and that is called the partition key, and so it actually identifies the row. From there, there's also a column key, which in this case is the email equals, or the first name equals, or the last name equals. The column key in SQL v3 is most often the name of the column that you configured in your create table. And then, of course, you've got the data on the other side. And so one of the interesting things, at least on this diagram, is that we didn't specify a value for Bob's last name column, so it simply isn't there. So in some databases, like that might actually take up space, the fact that there's a null in last name. Not a lot of them, but in some. That's definitely not the case here with SS tables. So now that we have inserted and updated data, and we've learned about how that works, let's actually try querying for some data. So in this case, it's a really simple query, as are most Cassandra queries. I mean, here we're actually selecting from the user's table via its primary key, and we're just getting it a row back. And just this is most often what you'll see for reads is very simple reads. There aren't anything like subqueries or joins or anything else in CQL. As I said earlier, the scaling concern has overridden some aspects of what people come to expect from databases. So there are some limitations that come with the kind of scale that Cassandra is built for.
Hey, Brent.
Yes.
So if you had modified the table in like one of your other slides to add that address
Yep.
map,
Yeah.
actually, so then when you ran the query like this, it would deserialize the results
Yep.
and show you something like a map.
Yep, exactly. What it would actually show in there is it would, first of all, it would have the addresses column, and then you would see a curly bracket and then a string being like home, and then a colon denoting that the value's up next, and then another curly brace with the components of the type in it. So I kind of left stuff like that out here just because I don't have a lot of horizontal real estate to play with. So, but yeah, it deserializes it all for you. And in most cases, with the types we talked about earlier, they print out as you would expect them to, except for things like blobs where it gets a little bit iffy. That with blobs, I think it gives you just the hex representation of it. All right, so what's actually happening when we do a read? So the first thing, we're gonna kind of skip the distributed aspect of it because we already went through that with the write, and with reads, it's pretty much the same thing. What I'm looking at here is from the perspective of a replica. So when a coordinator sends a replica a read, what is the replica doing is what we're talking about here. So first the replica gets the read request. From there, it checks a probabilistic set data structure called a Bloom filter, which basically tells it which SS table files it has that might contain data for that row key. Then once it's gotten a set of, and I say might contain data for that row key because Bloom filters actually will often, well, not often, but sometimes give you false positives. So you can always expect a Bloom filter to tell you, to never give you a false negative, but in some cases it will give you a false positive in so much as it'll tell you that an SS table contains data for a row key when it really might not. So that's actually something that's tunable in Cassandra on a per table basis. And I think it's Bloom filter chance. But anyways, once it's identified the SS tables that might contain data for the row key, the query is, sorry?
What if it's still in a mem table that hasn't flushed?
Yeah, I kind of left that out here. He makes a great point. What if it's already in a mem table? And if it's already in a mem table, it just comes out of the mem table. Yeah, that's the first, it's actually not on this diagram, and it should be. I noticed that a little bit late. Yeah, it actually checks the mem table first, and then it actually starts this process. So, good catch.
So what are the downsides to the Bloom filter returning a false positive? Once it goes to the SS table, it's going to see that the key's not there and just return nothing.
Yeah, it's gonna look for a compression offset. The compression offset immediately preceding where that row key should be in the SS table file. It's going to deserialize that, and once it gets to the first row key that's greater than the one that it's being queried for, it's going to give up. So you're getting, in the case of a Bloom filter false positive, you're getting an extra read, at least one, if not two. Depends on the partition index as well here. But the important thing to note about this basically is if you're already if the row you're asking for is already in the partition key cache, then you're only doing one sequential scan of the SS table file. Everything else that it needed to get there was in RAM. If the partition key cache didn't hold that row key, you're doing two scans, one on the partition index, which is on disk, and another to actually get the data out of the SS table. So it's very fast. I mean, some databases you talk about doing like random I/O all over the place, and doing seeks. Seeks are pretty slow. Sequential reading is pretty fast, and that's what you're doing here. Is basically a maximum of two sequential reads per SS table file that needs to be read. So once it's gone through this process of reading the data out of the SS table files that the Bloom filter has identified, it actually merges that data together. And so chances are there's some older SS table files for this table, for this row, let's say. Let's say this row has been updated, upserted to a number of times. And so maybe you first, upserted it, a year ago, and you later updated it or upserted it again just this week or whatever. So chances are there's probably an SS table file from a year ago out there with some old data in it, and there's an SS table file, from this week that has new data in it, or maybe a mem table. What I mean by saying that it merges the results is that it's taking all the different relevant data it's found for that row key, and then merging it based on what was the most recent write that I've got for that column. So it discards the old, or it gets rid of the old data and replaces it with whatever the newest data, the most latest data is.
configure the size of the node table? Or
Yes,
the table?
that is configurable. I haven't had to mess with it much or even really look at it. So, but I'm sure that's configurable on a per table basis. All right. All right. So one thing I just want to reinforce here, as I mentioned earlier, is there's a lot of constraints with CQL. Here, I'm showing one of them. Right. I'm trying to query a column that isn't in the primary index. And I see from SQL Shell, it tells me that there's no index columns present in my query. There's actually a solution for that, kind of. You want to be careful, but there are secondary indexes in Cassandra. So you can actually take a column that isn't already in a primary key, that isn't already a primary key component, and create a secondary index on it. And from that, you can actually write the same query again and actually get data back. You want to be careful with this, though. I mean, this isn't something you want to overuse, but it is available if you need it.
Hey, Brent.
Yes.
So if you had a multi-part primary key, so let's say you had username and email.
Yep.
So email is in, maybe it's my understanding, right, relational bias or whatever, but if email is in the second position of the key, can you search on it?
No. That's a good question. So Pitt is asking, let's say you have, well, yeah, it depends. Okay. So Pitt is asking if I have a composite primary key that starts with the first component being the username and the second component being email, can I query it by email alone without the username? And so the answer to that question is no, you can't. You have to specify each one of the components in the primary key. We'll get a little bit more in depth because there's actually you can split the primary key into two different other types of keys called the partition key and the cluster key. But yeah, you must specify both in that case.
So do you create a second index to create a whole key for it?
Yeah. So what's happening behind the scenes with the secondary index is what he's asking. And the answer is it's actually creating a hidden Cassandra table behind the scenes where the primary key is the email and the value on the other side is the username. So that's what it's doing behind the scenes. One of the reasons why you kind of want to avoid it is because of that. So what about actually deleting data? Here you can see the CQL for doing that. All I'm doing is just showing you that a username Bob exists, and there's one of them, and then I delete them, and now there's 0. But what's really going behind the scenes is a lot different than you might expect, and involves tombstones. So when you actually delete something in Cassandra, it doesn't get deleted. So there's no random I/O in Cassandra really. It doesn't go and seek to a position on disk where that value is stored and mark it as deleted. Instead, what happens is it writes a new tombstone record or new tombstone column to the replica that marks that column as having been deleted. So when we go through that whole process of a replica finding SS tables in the Bloom filter and then reading them, it will see when it reads that SS table file this tombstone, and when it sees the tombstone, it knows that it has to send back a result to the coordinator node that tells it that column is not non-existent, it's null. So the data, you might be wondering, that data that we deleted, it has to go at some point, right? It can't just stick around, otherwise the thing is just additive. You're continually adding more and more data without actually getting rid of the stuff you've gotten rid of. How that data gets deleted actually involves a process called compaction, which I just want to talk about real quick, kind of. So compaction involves taking more than one SS table files and merging them together and writing a new one and then deleting the old ones. So what you're doing is taking any number of SS table files and merging the data and writing out a new one. So there's actually two types of compaction. There's a major and a minor compaction. So with major compactions, those are actually triggered manually by running no tool compact. You actually have to do those on your own. And what those do is they will take whatever Cassandra tables you identify on that node and compact all the SS table files for that Cassandra table into one SS table file. So if you've got, let's say you've got like 5, 10 gig, SS table files on a node, and you tell it to compact them, if there's no deletes in those SS table files, if there's no tombstones, it'll write out one file that's 50 gigabytes, because it's 5 times 10. So that's what major compactions do, and they should be avoided because they make it a lot less likely that minor compactions will occur. And so when we look at minor compactions, what those are naturally, they happen automatically in the background. And how they actually work, though, depends a lot on the table-specific compaction strategy you set. But I'll just give you a brief overview of the 3 different types. I mean, there's size-tiered compaction strategy, which takes SS tables that are tiered based on their size. So you might have 3 different SS tables at 10 gigabytes, and those all get compacted up to the next level, which would be like 30, or whatever the setting is that you have for your tiers. And so that's size tiered. Date tiered is kind of similar in that you still have tiers, but it's not using size, it's using the window of time that the SS table encompasses. So if you have a 4-hour window, maybe you have 3 SS tables at 4-hour window of time, and you have 2 at the next level. It compacts every time it gets to like 4 on the same tier, and so that's size and date tiered. And then there's leveled, which ensures that data for a row is not overlapped in SS tables. So this is there's downsides to it, but one of the upsides is that it's really good for reads, right? Because that Bloom filter is only going to identify, hopefully, one file and no false positives. So it only has to scan through one SS table file when you use leveled. But there are downsides to it. It takes a lot of storage space and I/O time. Yes?
Question about the compaction, which you said was if it basically then just merges all the SS tables into the next larger table.
Yep.
But if the usage is that half the time there are updates to the rows, would it end up being compacted to half the size?
Yes, exactly. So when I gave that example, so you're saying, what if there are updates to columns across that are in overlapping SS table files? What if we update the same columns in 2 SS table files and we go to compact them? The example I gave earlier where I said, there's 5 SS tables at 10 gigabytes and you compact them and they'll end up be 50 gigabytes. That's true only if all the data in there was in regular insert, you weren't actually updating. If you did have columns that overlapped, you would yield space savings with that compaction. So it would be lesser than 50 gigs.
But is it correct? You would still have to have that larger complete size for it to do the compaction, to do the actual work, even if the end result was a smaller.
I guess I'm not sure. I guess you're talking about the compaction strategy, or just like
Well, it's trying to compact the 50 gigabytes down to the 25 gigabytes. It still needs 50 gigabytes of space to work that out.
Yes, that's true. Yes, and we'll get into that. There's a section later where I get into that, but a little bit. But yeah, you need part of running a Cassandra node entails that you make sure you have enough space to cover compaction, because what's happening is when you're doing these compactions and you're writing out this 50 gig SS table, that's in addition to the 50 gig you're already spending with the existing ones. So you're basically doubling the space that SS table, that Cassandra table is taking up. So yeah, that's a good question. All right, so just real quickly, example use case. Let's just say that we're running an e-commerce site that sells stuff, and we want to record interactions with our site for future analysis. So we want to see, what links people are clicking on, maybe for like A/B testing. Basically, we want to be able to analyze this data later and aggregate it. So let's assume we have some browser side code that will send us, page views, hovers, clicks, and other events, and that it's our job to model the Cassandra tables and queries that the server side component that browser is sending events to get persisted with. So let's look at first an event table that stores some of this data coming from a browser. So first off, I'm keying it, based on, you can see the primary key here is username and time. Username in this case acts as what's called the partition key. So it's the actual key the row key that's being used to store SS tables. Okay. The time column acts as what's called the cluster key, and so with the time column we can actually perform range queries against it, as we'll see a little bit later. And then this table also has a params column, which is just the map collection data type that allows you to, in this case, specify some properties with the event, what product page it is, that sort of thing. So let's look at some of the writes that we're doing as part of our server. So let's say Alice goes to the home page, so we're inserting an event that the browser sent us, and the data might contain Alice as the username partition key, and then the timestamp as the cluster key, and then you have a page load type, and then the map value you see here with the curly braces that specifies the URL that's being loaded as far as the page goes. And then you also have similar inserts for hovering some product links. So the only difference there is that the type of that event has changed from page load to hover, and our params for that have changed to include the product ID of the links that they're hovering. And then finally, let's say she clicks on the super mega widget product page link and ends up going to loads the page here for it. You can see the page load event. So what about actually querying these events that we've just persisted? So real simple, same thing as before, we're querying based on username. So this time we're counting all the events for Alice. But the next query is a little bit more interesting because it's new. It allows us to find all events for Alice within a given time range. So in this case, the time range I've sent includes the two middle events and excludes the one that started it and the one that ended it. So you're seeing a time range query here with CQL. Time range or time series data is kind of like one of the specialties of Cassandra, one of the sweet spots in terms of use cases for Cassandra, because of queries, because of the capability to perform queries like this.
Question.
Yes.
Conceptually, why do they call it cluster key? I understand why they call the username partition key.
Yup. Because what you're doing with the cluster key is you're clustering columns that are in the same row, and so that's why it's because you're clustering them in the same row. Even though in CQL they appear as separate rows, what's actually happening in the storage engine is the SS table file contains one row for per SS table file for that key, and the cluster keys are all contained within that row. So, yep. So just a couple things about what CQL does not do. And I've kind of mentioned some of these before. With CQL, you don't have access to joins. So doing a join against tables, partitioned across many nodes is way too expensive, and that's not really Cassandra's sweet spot, what it's doing best. Instead, when you find yourself needing a join, oftentimes you have to look at ways of denormalizing data to sort of get around that lack of join. And that's one thing that's very much encouraged. There are also no subqueries with CQL, so you can't do crazy things like scalar subqueries or joining to a subquery or anything like that. Cassandra tries to stick to one thing, and that's storing and retrieving key partition data at scale. Subqueries are a pretty big distraction from that. Oftentimes, what you'll see, for this and also for joins, for subqueries and for joins, a lot of times what you'll see is solving the problem in your data layer, in your app-specific data layer. So like with Womply, we have a REST API that exposes all of our Cassandra data, and a Rails app calls into it. That REST API, the implementation of it, in some cases is issuing multiple SQL queries to return one logical REST API response, because we've had to denormalize, and the denormalization often skews you off of something like a REST interface. So there's also no group buys. So whenever you need to aggregate data sets, it's usually done pre-computed. They're usually pre-computed and stored in their own tables. You probably want to consider something like Spark Streaming or Storm to get sliding windows for these types of aggregations, but Cassandra can definitely act as the storage component of such a setup, and often does. So let's just look at real simple. Yes?
Just to be clear, it's not simply CQL that doesn't do it, it's Cassandra that doesn't do these things.
Yeah, I say it's CQL because that's the only thing that I'm comparing CQL to SQL, but yeah, it's Cassandra and CQL and by extension Cassandra. Yeah. Yep. So one thing, another quick example. So if we want to do real-time aggregation, let's say we want to graph all the product page views in real time. Plot a graph that has a line for each one of our product pages over time and how many page views they each got. Each data point could be whatever interval you wanted them to be. In this case, let's just say it's 5 minutes. What might the table look like that Spark Streaming and Storm persist to? You can see the create table here. I'm calling it event time series. It has a partition key, which is the first part of the primary key statement there, the date. The first part of that primary key is always called the partition key, and it ensures, in this case, I've chosen the date, but then I've also got time, which is a timestamp underneath. So this looks like denormalization a little bit. I mean, I'm replicating, or I'm copying the same data in multiple columns, and it seems a little bit ugly. There's a reason for it, though. So if we got rid of the date column, right, and we just had time, what we would have is what's called a very wide row. We would have basically that one row it would be one very skinny row, because we would have to always query by the timestamp. We couldn't do a range query, is basically the problem. We would always have to query for a very specific time down to the 5 minute aggregate that we're looking for, and that's obviously not what we want. We want to be able to ask for many data points with a range query, and by adding this column as the partition key, we're able to do that. We do have to specify what date we're interested in, but then after that we can specify either the upper or lower bound of the range of time that we're interested in for that date. And this is another example of why you often find people creating data layers around Cassandra, is because you would, in order to go over multiple dates here, you would have to issue a query for each date that you're interested in. Generally speaking, you could do that in an asynchronous way. You could issue all 30 of the queries for a month at the same time and merge the results when you get back. That's a pretty common thing. But nonetheless, it's something that needs to be done in order to allow for a range query here. And then from there, you just have a map containing the product ID to the page view count for that product ID. So
With something like that, where if you go back to a real web page went to the 5-minute increments you have.
what's it, say that again?
So if you go to a table like this, where instead of 5-minute increments you have millisecond increments.
Sure. Sure.
How big can you generally allow? How wide can you allow a row to get before the search function within a row becomes sufficient?
Sure. It's pretty, well, generally speaking, I like to stay under like 10,000 rows per query. It's a very arbitrary number, kind of. But when I go about actually writing primary keys that require this kind of partitioning, I often try to stick to under 10,000 rows for time series data like this. But it really depends on what exactly is in the table aside from the primary key itself and how much data there is. You can have much wider rows than that. It used to be back in the day that with CQL client libraries, you couldn't query beyond a certain point, otherwise you would get a read timeout. Like it would stop scanning at some point because it didn't want to send all the results back to the client. Since then, they've implemented cursors, which allow you to ask for a ton of rows, out of a very wide row key, and still receive those results without any kind of timeout. But yeah, it really depends on the use case and what you're storing in there, is what I would say. All right, so now let's talk about just real quickly some analytics options. I mentioned earlier that you can run Hadoop against Cassandra. It is pretty painful to set up if you go on your own. I wouldn't recommend attempting to, add Hadoop support onto like a DataStax Community Edition. Instead, I would, if you really want to go with Hadoop, I would say best to use DataStax Enterprise and go with their support there, which is pretty good as far as Hadoop goes. If you do go the DataStax Enterprise route, they support MapReduce, Hive, Pig to varying degrees. I had some pretty weird experiences back in the day using Hive and Pig with Cassandra, but hopefully those have all been worked out in the year since. One thing to note about Hadoop is like if you go to the Cassandra Summit or the Cassandra meetups out on the West Coast, there isn't a lot of talk about Hadoop and Cassandra, so that's what I'm the one saying this here. That's my interpretation, but in my opinion, as far as Cassandra goes, I mean, like Hadoop is pretty much all but deprecated.
Can you say a little bit more on why that is?
I would say that for the most part, it's because of the emergence of Spark, which kind of leads me into the next set of bullets. Apache Spark, that's actually what we use at Womply. So whenever we need to do analytics, we're Spark based. We used to use Hadoop back in the day, but I basically ported everything over to Spark because I enjoyed it so much. But Spark doesn't require DSE, the DataStax Enterprise. You could run it against, the DataStax Community Edition. And when you go to write your Spark jobs, what you'll use to integrate with Cassandra is the DataStax Spark Cassandra connector. I got Spark in there twice in the bullet, but whatever. It's the DataStax Spark Cassandra connector. It's basically if you haven't used Spark before, Spark, you have choice between Scala, Python, and Java right now to write your jobs in. The DataStax Spark connector is in Scala, so I'm not sure if you can write jobs in Python, but at least you can in Scala, and probably Java too. And just personally, I really recommend using Spark for doing analytics with Cassandra or whatever data store you're working with. Chances are it'll probably be a good experience for you, I imagine. It definitely has been in my case with Cassandra. some analytics best practices. You want to make sure that you ensure good data locality. What that means is running Hadoop or Spark on the same nodes that run Cassandra. So the Cassandra Hadoop input-output format and the Spark connector are both aware of data locality. So they know that this Hadoop task or the Spark task is running on this particular machine, and it knows enough about the key ring to know what keys are available on this particular node. So data locality works in your favor there. It's also a good idea to keep data centers that are doing analytics separate from the ones that might be serving up query results for your site. You really don't want to have some analytics job contending with the response times for your site. So it's often a good idea to separate those two, and you can do that by having two different Cassandra data centers, as we talked about.
What does OLAP and OLTP stand for?
So OLAP is kind of the old school, like online analytics process.
Transaction processing.
Yeah, and OLTP is online transaction processing. Yeah. Yep. So when I say OLAP, I mean like Hadoop or Spark. And when I say OLTP, I mean like your web app is querying your database and you need results right now. So another good thing to do is spend some extra time ensuring that you're using system resources effectively without trampling on each other. And what I mean by that is trying to get Spark and Cassandra to run on the same nodes. There's a lot of contention for resources there. You just want to be extra careful about planning. Chances are using a resource manager like Yarn or Mesos could help, but I'm not sure about that myself, just because we're just running Spark standalone for now. But definitely looking into Mesos. So just some miscellaneous administrative stuff, DevOpsy type things. Each node you want to have run the node tool repair -pr command on a regular basis. This is what's called a rolling repair. Basically, it tells the nodes to, in the background, with an eye towards throttling the usage of the CPU and I/O, to go about making the cluster consistent. So when you run node tool repair, what's happening is you're telling that node to check with the other nodes to see if there's newer data for the parts of the key ring it owns. And so Cassandra actually throttles that. It's a behind the scenes process. It's something that's often running and doesn't consume many resources, so it's all right. Another important thing is make sure you have your clocks all set accurately using something like NTP, just because if you don't, Cassandra might think that a write came in earlier or later than it really did, and that would conflict with other nodes. So you want the nodes in your cluster to all have pretty accurate clocks. The data directory that Cassandra writes these SS table and SS table files and commit logs to, or the commit log to, should always be on local, hopefully solid state drive storage. You never want to use like a storage area network for something like Cassandra. You want to keep it on the local storage for that machine. And you can do that by leveraging Cassandra's just a bunch of disk support. So Cassandra can take, if you have a machine that has multiple disks and you want to have Cassandra store its data on it, it can manage those multiple disks using its JBOD feature to actually achieve concurrency, to be performing multiple writes at the same time, and also spread your data across all those disks. Or the other option, what I chose to do is run RAID 0. So I just have Linux take two different block devices and merge them into one logical volume, and then Linux, the kernel actually goes about worrying about what block is being written on what device. So it works out really well for me because I can use that storage That's one logical volume. RAID levels above 0 really are unneeded. So what that's saying is if you have a disk failure or something, you should probably just mark that node as down and migrate to another or add another node to replace it, rather than worrying about RAID controllers and having to repair a failed disk. Cassandra is really meant to run on commodity hardware, so RAID levels above 0 are really frowned upon. As we talked about earlier, compaction requires extra available storage, so it's 50% available storage in the worst case for tiered compaction. 10% for level is the worst case there. So you want to make sure that you always have enough storage to cover your whatever your compaction strategy is. And finally, read and writes operations per second should scale linearly, meaning that if I'm getting 1,000 or 2,000 writes per second with one node, and I add a second node and with the same replication factor, I should get 2 times the throughput. So I should be seeing 4,000 writes per second. And if you add more nodes, you should see that scale linearly for your read and write ops. And that's exactly what you see here in this graph. Is Cassandra's represented in the blue. This is actual data from somebody who benchmarked it. I want to say it might have been Netflix, but I'm not sure. But what you can see here are, Cassandra in blue. Basically, as you add nodes, you're seeing, a linear improvement in the operations per second there. This particular graph, I think they were doing both a mix of reads and writes, but whereas with some other databases, the improvement you get degrades as your cluster gets bigger. So it's kind of the holy grail of scaling. So lastly, if you want more info on Cassandra, you can look at DataStax's developer site. A lot of the diagrams and stuff that you saw in this presentation were lifted directly from that site. So a lot of good documentation out there. There's also Planet Cassandra, which has some good stuff, including like a list of the different SQL clients out there available in different languages. One thing to caution you against is to be aware of old documentation, because a lot has changed. Over the course of Cassandra's development, there used to be something called Thrift. Well, some of you might have heard of Apache Thrift. There was a Thrift API in Cassandra that's since been more or less deprecated in favor of the SQL binary protocol I talked about earlier. So you really want to avoid Thrift and kind of stick to the CQL version 3 documentation when you're looking around. So that is it. Any other questions I can answer for anyone?
Back to the coordinator, client calling coordinator. If the coordinator knows right away that they can't meet the consistency, does it return right away? Or does it wait for a node to come up? Like if it's going to wait for more?
Yeah. So if the coordinator knows that there are no replicas available, not enough replicas available to meet the consistency level, and you're not using the any consistency level, then it would return right away. Yes.
Can you tell us a little more about your physical setup? You said you guys have Rails and Cassandra.
Yep.
How many nodes?
I can't get into specifics to our cluster just because my boss told me that's kind of off limits, but I can tell you that we do run on Amazon EC2 instances, and our basic architecture is we started off as a Ruby on Rails app that used MySQL about 3.5 years ago. Since then, we found aspects of our MySQL database usage not being able to scale with it. So that kind of prompted us to look into Cassandra 1.5 years ago. And we continue to port more of our MySQL data tables over to Cassandra. So yeah, it's Ruby on Rails talking to either MySQL or a REST API that it acts as a wrapper around our Cassandra cluster. Yes.
Do you use any other NoSQLs to complement what Cassandra does well with something else that does something else well?
Sure. The question was, do we use anything other in the way of big data stores other than Cassandra? Right now, that's not the case. We only use Cassandra. However, we are beginning to find use cases for other data stores that might fall under the umbrella of NoSQL, particularly Neo4j. There's also a graph database out there that actually uses Cassandra as its storage engine that we're looking at. That's called Titan. In fact, DataStax, which is the company that sponsored this, they just bought the startup that was behind Titan. So there's a definite direction for Cassandra to start supporting these graph database types of use cases. Yes.
While you define the consistency levels, you didn't really talk about how they're used and defined. For the company that I worked with, one of the things is that you would have a quorum for the writes, but you'd have just one for the reads.
Yeah, that's pretty. So most of the data that we're getting comes to us. Are you talking about Womply specific consistency levels, or just in general?
In general.
In general.
I mean,
Yeah.
you covered definitions,
Yeah.
but you didn't say really how they're used.
Yeah, specific to reads and writes. Yeah, it was kind of specific to the write part of it, but not the reads. So yeah, generally speaking, when you do a write is when you want to ask Cassandra to persist at the quorum level or something a little bit higher than on the reads. It all depends on your use case, though, right? I mean, what kind of consistency do you really want to expect? And then that's where I'd have to leave that up to whoever's implementing it.
Does anybody use the consistency level of all? All pretty much.
I don't hear many people using it, but I'm sure, I don't know, maybe in some financial services.
Well, I mean, all is equivalent to using a regular relating
Yeah, all
database.
Yeah.
great.
It costs you much more time than what you're supposed to be buying by using Cassandra.
I was just wondering why it's there.
So you can do that and get some money.
I suppose.
Actually, Netflix did a study a few years ago about, they called it eventual consistencies not equal to hopeful consistency. They created 264-node data center, or two clusters, right? 64 nodes, and they went ahead and they did 1 million writes at consistency level 1, and watched them all replicate in the other data center, and went and read all 1 million of them back and didn't lose a single one. So. And that's Netflix, who does what 3 trillion transactions a day or something?
Yeah, something crazy. Yeah, they're a big proponent of Cassandra. By far the biggest user that I know of. Any other questions I can answer?
What tools did you use? Like, are there any recent books or just go to the website?
Mostly the DataStax developer site, I would say, is probably got the most up to date and complete information out there. Other than that, I haven't used many other resources, to be honest with you. Yeah. Yes, sir.
As a developer, the idea that these are tables and rows and all that, it is okay from a high level, but once you start working with it, that's not all what it is. It really is the column.
The storage engine is, CQL is a pretty dangerous thing in a lot of people's opinion because it gets so close to SQL that people start to think that that's what's under the hood, and it's totally not.
Yeah, and one of the things I wanted to say was that when I was researching it, I really had to look at some of the other people there's some really good diagrams and descriptions as to what's actually happening with Cassandra as far as primary key. It's the reason it has to be a literal exact match is because it's a hash.
Yep.
To get to where you're going, which is
Yep.
how all these other things happen so quickly across the nodes and everything.
Yep.
And the writes and everything else. And if you want to delve all the way down into how much data is written for each of the different records, you get into, all the keys are there as well. So there's a lot that's not covered in this presentation.
Yeah. This is actually my first presentation.
If you're a developer and you really need to worry about these things.
Sure, yeah. I tried my best. This is actually my first presentation on here, but I definitely would agree. There's a lot to learn with Cassandra, and gonna have to beef up your knowledge a little bit more as well. So.
Is Facebook still using Cassandra?
I'm not sure exactly. I thought they used it initially for some sort of mail function, I believe, when they actually started with Cassandra. I'm not sure if they still are though.
Earlier in the slides, you had said when you create an index, it basically makes a one-one map table in Cassandra that maps that index to the primary key. Does that mean that the indices have to be?
Is there a list on the value on the non-primary key side? Is that what you're getting at? Like if you have multiple? Yeah. So I'm pretty sure the way that the only reason that I know that there's a table behind the scenes is because you can actually see it in the data directory on the SS table tables that you see. There's actually a table that starts with IDX and then whatever your table name and column are. As far as multiple rows in that, or multiple values, like if you have 2 records with the same email address, those will be picked up by a select that goes against the secondary index. I'm not sure like what limits there are though on when how many rows can have that same email address before the secondary index becomes too poor to use, I guess, too big a performance degradation. So it's secondary index. We only use them in our system for looking up. Basically for things that you would do manually. We don't use secondary indexes as a means to do something that we have to automate. It's basically we would use a secondary index if, for example, we have a feeds table and we have a secondary index on the file name. That's something that we would do manually. It's not something that's actually done by the system itself.
Is there a limit on the size of the composite key?
As far as columns in Cassandra go, there's a global. I think it's 2 gigabyte. 2 gigabytes is the max columns or row size, or no column size. As far as rows, I'm not sure, but it's something crazy. And as far as the actual text inside your row key, I would think that the column length restriction applies there and nothing beyond that. It makes for a harder value to index on, though. Yes?
You also didn't really cover the other usage scenario. You talked about it with respect to relational databases, but you had mentioned wide rows.
Yes.
But never covered those.
Yeah. There's wide rows and skinny rows, and it's a consideration when you're modeling your primary keys. Oftentimes, to prevent, if you want to prevent too wide a row, like if you're doing a range scan against a wide row, oftentimes people will add another column to the partition key so that the length of the row becomes a little bit skinnier, like the per day thing that I added to the time series table sort of shortens that row length to make it a little bit more skinny, but yeah, there are differences between the wide and skinny rows.
Well, I guess what I was getting towards was the fact that each of the rows can have any kinds of columns you want to have. It's not a relational database where every row has these 5 columns.
Yeah, that's true. Yeah, altering a schema or altering a table is easy because of that. It doesn't have to go through and actually.
Well, and every row can have absolutely differently named columns.
I try to get at that with the SS table diagram, or the row boxes that I had going on there, but it was a very limited example. But yeah, you're right. Yes?
Are you providing services to small businesses?
Yeah.
How they are leveraging it?
Our product is basically one of our products is a dashboard for small businesses, merchants like restaurants and, all manner of different types of merchants. We give one of the products as a dashboard, and it shows, for the most part, time series data. based on the revenue that they've had at that business. And we also, merge in data from like social networking sites and weather. So yeah, that's the product that we're selling to merchants via a telesales force. So we have a distribution channel for selling our product, and we have people. So we get leads from financial services companies, and then call those leads, walk them through our dashboard, and hopefully they buy the product. That they subscribe to it. What's that?
Is that a cloud-based solution?
Yeah, I mean, you could consider it. I mean, we're sort of a software as a service type model. People subscribe to our dashboard and to the emails we send out, because we also notify them when certain things happen as far as reviews, like if you get a bad Yelp review or something to that effect, and also their revenue on a weekly or monthly basis. They get a summary of it via email. So yeah, it's kind of a software as a service type of product. Yep.
How does it guarantee consistency with the indexes, since they might be on different nodes than the node responsible for the front?
So the index is actually tied to the SS table file. So when you actually look at SS table files in the data directory, you'll see several different types of SS table files. There's a data file, which is kind of what we focused on in some of the stuff. There's also an index file, which is identifies the offsets in the SS table data file. So it's a per replica thing. The index isn't detached from the.
I meant the secondary indexes.
Oh, as far as secondary indexes go, and the question was again?
Since the index that needs to be updated for a particular column might
Be different than the node that it's on. Yeah. So I'm not entirely certain like what the distinction is there, but I only know from a user's point of view. I'm not sure what the internals are as far as how does it ensure that the index gets updated directly with the SS table data directory. So I'm not sure, or the SS table file. So I'm not sure there.
Other questions? Yeah. Using Spark, right? You said you're using Spark.
Yep.
Scala. So are you using Phantom? As a client, just Cassandra?
Yeah, it's interesting you bring that up because I'm actually working on a blog post. I want to sort of demonstrate with this blog post like how we're trying to do sort of test-driven development with our Spark jobs. It's kind of weird, but like some of these Spark jobs get kind of complicated, and basically I want to ensure that they're working the way we all expect them to. And as part of that blog post, I'm using Phantom and Scala test. So I actually use Phantom to insert data to Cassandra tables. I run the Spark job, and then I use Phantom to make sure that the data in those tables matches what I would expect, based on the requirements. So yeah, we do use Phantom. We're considering more widespread usage of it. For now, our REST API is written in Java using Jetty and the DataStax Java driver. And I've got like kind of a layer around the driver that allows me to use things like models, serialized data in the models and stuff. But yeah, so Phantom is really cool. We really want to use it more widely, replace the REST API we have with a Scala-based implementation and use Phantom as part of it. But it's one of those things that's kind of on the back burner. Yeah, spray can is what I'm using for the proof of concept. There's also Play, but generally what I've seen, at least just looking at the two, is that Play is more like MVC based, whereas spray can is. Yeah. Yeah, so spray routing works pretty well with the I also write in specs, for the REST API that we're doing with Scala, and that the specs for using spray routing have been pretty awesome.
Has the community improved? When I was working with Cassandra last year, it seemed like really the only way you could get support or feedback was if you had a direct line to data specs.
Um,
Even their documentation was more higher level and not so useful in the nitty-gritty to get things working.
generally speaking, I know what you're saying. Data Stacks is usually the end-all be-all for a lot of people using Cassandra, especially people with money.
Well,
I mean,
that's it, they're for pay.
sure. At the same time, we are using DataStax Community Edition. You know, what experience I've had with the community has been a good one. You know, I go out to San Francisco and go to some of the meetups out there. I've been to the summit. You know, when you get away from, you know, some of the DataStax sponsored, well, no, the DataStax centered stuff, and talk to some people using it, my experience has been good. So I'd have to say, yeah.
But even like on Stack Overflow, there's almost nothing about
Yeah, I haven't had to surf Stack Overflow a lot for some of the stuff, but yeah, my experience with the community has been pretty good, albeit, you know, I've
Planet Cassandra or through planetcassandra.org or
I haven't, to be honest with you, I mean, I haven't gotten really into becoming a huge part of the community. At the same time, my building solutions that use Cassandra has been something that's I've found at least pretty easy, even though I'm not paying for something like DSE or support contract or anything else.
Okay.
I guess the docs have been enough for me for the most part.
There's a lot of good feedback on the Google mailing list for Cassandra. You can find on the project site. And as far as Stack Overflow goes, I probably answer about a dozen Cassandra questions a week on Stack Overflow. So I know there's some people out there.
All right. Well, thank you guys very much.
Thank you.
Tried my best, man.
Yeah, you did a good job.
Nice presentation.
Well, thank you. I appreciate it. Good job. Good job. Good presentation.